Our understanding of a force in physics was pretty murky until Sir Isaac Newton formulated his laws of motion. And so we can see the three of them listed here. We have the first law, the law of inertia. Speed of a body remains constant unless the body is acted upon by an external force. So more common way of saying it is a body at rest stays at rest, body in motion stays in motion unless acted upon by an outside force. The second law, which will be our point of emphasis in this lesson, is the acceleration of a body is parallel to and directly proportional to the net force applied to it. And so the key here is that it's a proportionality statement. It is not an equal statement, even though we always use F equals ma. And so we're going to explore that idea a little bit because it becomes a little bit more complicated for us, not when we're working in SI units, but when we're working in some English units, which we have the joy of experiencing because we live in the USA. And then the third law there, for every action there's an equal and opposite reaction. We'll take a look at that one, that law in a separate lesson from today. But focusing in on the second law, again, it's a statement of proportionality. F is proportional to ma. So that means that to get to an equation, we have to know a constant of proportionality that allows us to transition to F equals ma and then use that equation going forward. Now, suppose we have a force F1 that accelerates a mass m1 by some acceleration a1. So we have some set of units for which we know all of these measures. So again, we can say that this is a statement of proportionality like we see here. And so we can eliminate the proportionality by taking the general statement F is proportional to ma and dividing it by this known set of units, this known set of quantities. And so that's what we see here. And so then we're just going to isolate the F in this equation, so not F1 but F. And so we've got this F1 over M1 times A1 times MA. And so this collection of measures is the proportionality factor 1 over G sub C. And so any consistent set of units for this G sub C is going to satisfy this equation. So as long as we have a relationship between some known force and some known mass and some known acceleration, then we can plug those numbers in to create this relationship of proportionality. Now, it's in our interest, if we want to have as simple an equation as possible, for this G sub C to work itself out to equal 1, so that we can end up with F equals ma, the way we commonly refer to the second law. In this example, we have an F1 equals M1 A1 relationship given to us that we're going to use to create our constant of proportionality to then solve for some new force based on a new mass and a new acceleration. And so a slug, so that is indeed a mass unit, so one slug is defined as being the amount of mass that will accelerate at 1 foot per second squared when a 1 pound force is applied to it. So you can see that we've got a series of ones here. So if I rearrange this into F1 over M1 A1, then we're going to still equal 1, and all of these units are defined to cancel each other out. So if I write the F equals ma with this constant of proportionality, we'll include it this time. So again, F1 over M1 A1, so this is our 1 over G sub C times ma. So we're trying to solve for this weight, which is of course a force. So that's our unknown here. And I'm going to plug in all of these values here into our F1 over M1 A1. So I've got my 1 pound force over 1 slug times 1 foot per second squared. Now my new mass is this 5 slugs, so I'm going to plug that in for m into my F equals ma with the constant of proportionality there. 5 slugs times, here's my new acceleration, 32.2 feet per second squared. Now if we take a moment and pay attention to the units here, my feet per second squared are going to cancel, my slugs are going to cancel, and so indeed I'm going to end up with my desired units of force, 1 pound, pound force. So all I have to do now is multiply 5 times 32.2, everything else is a bunch of ones, and so we get F equals 161 pound force. So here is an example of a unit system where this slug is defined as the amount of mass that when a 1 pound force is applied to it will accelerate at 1 foot per second squared. So that allows us to have G sub c equal 1, which means we can basically ignore it and go straight to F equals ma. This is what is going to happen when we're in SI units as well, as we'll see in just a moment. Now, the problem with this is no one uses slugs. So we don't have a good intuitive sense as to what exactly that mass amount is. That's where we're going to work with SI units. But we still work in English units. We just use a different mass amount. But when we use that mass amount in engineering English units, our G sub c value we'll eventually see is not equal to 1. So this is why I'm bringing this up, is to make sure that we understand that it's not just a default F equals ma, it's F equals 1 over G sub c times ma, but it's just that in SI units, or in this slug system, G sub c happens to equal 1, so we're left with just F equals ma. In SI units, forces are measured in newtons, mass in kilograms, acceleration in meters per second squared. So the relationship between those three quantities is that, just like with the slugs, if I have a force of 1 newton acting on a mass of 1 kilogram, it's going to cause that mass to accelerate at exactly, I've written over it here, but 1 meter per second squared. So just like the slug is tied into a pound force and a foot per second squared, so too is the amount that of a kilogram. It's so that when we apply 1 newton force, it's going to accelerate at 1 meter per second squared. So these quantities are not by accident. They are defined together so that we'll have this G sub c, this constant of proportionality, equal 1. So we again end up with F equals ma. And so we can see that here. It's all ones. We've got the 1 kilogram, we've got the 1 meter per second squared, we've got 1 newton. Now you notice I have it upside down here because the F1 over M1A1 is actually 1 over G sub c, but the broader point still remains. We end up with ones everywhere, and all these units cancel each other out since a newton is defined as being a kilogram meter per second squared, and so we can just ignore that constant of proportionality when we're operating in SI units and just write F equals ma. So for the example that we have in front of us, we've got a mass of 250 kilograms with 3 significant figures. We have a acceleration of 7.50 meters per second squared. So we can go ahead and multiply those together and get 1875. But again, with 3 sig figs, we're back to that. We're going to report our answer as 1,880 newtons, which is the force unit in SI units. So again, in both the slug system and in the SI system, G sub c, we just have never even thought about it because it always equals 1. The units are defined in such a way to make that happen, to make it so that we can just use F as equal to ma without having to worry about a constant proportionality.